Sir, you are muted.
Thanks for pointing that out. That was a bit stupid of me. So it was op-amps and JFETs, right? That was what was a declared topic for tomorrow's class test. Not oscillators. Oscillators are too recent. Is that right? I can of course check my mail, but does anybody remember?
Yes, sir.
Yes, sir.
Yeah, op-amp.
Yes, sir.
Okay, so these are the correct topics, right? Op-amps and JFS. Fine. So if anybody has any questions specifically about these topics, please go ahead. If not, I can always talk about what is going to come in the next lectures. So everybody knows everything about op-amps. Great. I've understood everything that we have discussed, right? Is that true, or nobody even got to see those videos?
Sir, in one of the lectures you were discussing the unity gain amplifier. I didn't understand what was the purpose of that.
Okay, that's a decent question to ask. So let me just remind everybody that this circuit is called a unity gain buffer or a unity gain amplifier. As always, even if the inputs are not marked in an op-amp, the upper input is a negative one, the lower input is a positive one. And the way this works is, as long as the op-amp is in the linear region, VD has to be approximately 0. VD, remember, is V plus minus V minus. Here, V plus for our thing is VI. So V minus is also VI, or almost exactly equal to VI. And since V minus is shorted directly to the output, this implies VO is also VI. So for this circuit at least, the output is exactly equal to the input. And so this is why the gain, of course, is 1. So this is why it's called unity gain. That part is easy to understand. The buffer, the rest of the nomenclature, that's exactly why we use it as a buffer. So we are going to understand what buffer is. But let me just remind you before that, if you had a resistance here, for example, would the resistance have made a difference? So instead of shorting the output to the negative input, if you had put a resistance in between, would that have made a difference?
So I think no, because no current flows through that branch. So I think no effect because no current flows through that branch.
No what flows through the branch?
So no current flows through the branch.
Right, exactly. So at least for all practical purposes, the current flowing through this resistance R would be negligibly small, because that is the current which would be entering the negative input of the op-amp, and that's very, very tiny. Okay, so because the current flowing through R is very, very tiny, unless you go overboard and connect, say, a giga ohm order resistance there, the resistance will really have no effect. But let's say I connected 2 resistances like this, R1, R2, and grounded the R1. Do you recognize what this circuit now is? This is a very familiar
non-inverting amplifier.
This is a
non-inverting
could you just repeat that? Okay, this is exactly a non-inverting amplifier. The second kind of linear circuit you can make with the op-amp. When I say second kind, I mean the second that we studied after the inverting amplifier. And the gain for this is 1 plus R2 by R1. Note that in our original circuit, R2 was a short, so it was 0. And there was no R1, so there was an infinite resistance between this point and the ground, so R1 was infinity. So 1 plus R2 by R1 definitely under these conditions would have reduced to A equal to 1. So you can actually think of this not as a separate circuit, but simply as this non-inverting amplifier with the special condition thrown in, so that it's going to give you a gain of 1. Of course, that doesn't answer the question as to why you would want to use it. The answer to that lies in the following. How much current does this circuit draw? That is at the input. This is the input, right? How much current would flow in from an external? Of course, you have to connect an external signal or some other part of your circuit to this in order that this works, right? You can't, if you had a floating VI, that would of course not amplify anything because you're not giving an input. But if you gave an input, you would have to connect something for that. And how much current would your circuit draw from that source?
So negligible.
Negligible, right? Because same reason, the plus end almost draws no current. So this circuit has a huge input impedance. Okay. What about ZO? ZO is the output impedance, which basically is the output impedance of the op-amp, which is tiny. So what you have here is a circuit which does not change the voltage at all. VI is the same as VO. So no advantages as far as gain is concerned. It is exactly unity gain. That's part of the name. But it has a huge input impedance and a tiny output impedance. So why is that a useful thing? So for example, if you have this, suppose I had this source, say, it could be a DC source, could be an AC source, because the op-amp can actually amplify DC rather well, as we have seen. But suppose it has a 500 ohm internal impedance. And you want to connect it to suppose this could be a microphone with a 500 ohm internal impedance. And you want to connect it to a speaker. This is loud enough, you don't want an amplifier in between. Or maybe this is the output not directly from a microphone, but this is the output from a amplifier system. So it's loud enough. It should go to a speaker. And let's say a speaker itself has an input impedance of say 50 ohms. So that's the 50 ohms here. Now suppose you're going to join them together directly. Notice that your input signal, whatever that is, gets dropped now across a series combination of a 500 ohm resistance, which is the speakers, which is the microphone's own impedance, and 50 ohms here, which is the speaker's impedance. This, of course, although I've shown it as separate from the speaker, this really is inside the speaker. So now, whatever signal you have, the output voltage, the voltage across the speaker, will simply be 50 by 550 times Vs. That is, you will get a huge cut down in the voltage. So even if your microphone produces big enough signal, or maybe you had an amplifier which was producing a big enough signal, the output may be very small compared to that. That is one problem, but the other problem, as we have kept on emphasizing over and over again in this course, is that in this scenario, the thing will be strongly dependent on what signal you use or what microphone you use and what speaker you use, right? Because if you change your speaker, the impedance of the speaker would change, and that would strongly impact on how much output you will get. If you change your microphone, the same thing will happen. So this is a situation where if you directly couple your output to whatever device you want to send it to, you may end up with a big problem, because you end up with a situation which depends on specific details of external circuit components. Not a good thing to have in an actual circuit. Okay. Of course, the problem that the gain drops a lot simply because most of the signal is dropped in the internal impedance of the signal is also a huge issue. But even more than that, perhaps, is the fact that this whole thing becomes very fickle. It depends on whatever external components are connected. Now, why does this happen? This happens because the internal impedance, the input impedance of your speaker is tiny, and the output impedance of your source is huge, right? Remember, we talked about this often enough for when we discuss amplifiers. You want the input impedance of your amplifier to be big or your device to be big compared to the source impedance. Here, the opposite might very well happen. Now, how would you handle that? You handle that basically by putting this circuit in between. So this is your unity gain buffer. So what does that do? The unity gain buffer hardly draws any current whatsoever, right? Because of the huge input impedance of the op amp. So no current drawn inside, almost no current drawn inside, which means almost no drop across this resistance. Doesn't matter whether it's 500 ohms or 10 ohms or 5 kilo ohms or mega ohms or whatever. Very, very tiny current goes in because of the huge input impedance of your circuit, the unity gain buffer. As a result, whatever you are giving here, whatever your signal is, almost the entire thing is the input. And because VO equals VI, the output is almost exactly that. And now that output gets fed across the speaker. And the issue is the output from the op amp, which has a very low output impedance. So basically, the point is this: if you want to couple large impedance source to low impedance load, you should not do this directly. As we discussed, if you do this directly, you are going to get into trouble because essentially because there will be a large drop in the loads, in the source's resistance, and also, of course, because you have fluctuations if you change your source or load. You would connect them through a unity gain buffer. The job of the unity gain buffer essentially is to isolate or act as a buffer between the source and the load so that it manages to take the input from the source without drawing any current from it, so without affecting the source, and manages to supply the output to the load. This input gets supplied unchanged to the load, but at a very low output impedance so that the load's resistance will not affect the output. Is this clear?
Yes, sir. Understood.
And one of the major uses of this kind of unity gain buffer would be in circuits like this. We talked about this when you want to do calculations, for example. Suppose I have 1K, 10K. Now this circuit, how much is the gain of this circuit? I shouldn't really have to ask what circuit this is, but how much is the gain of this circuit?
-10.
-10, right? So if I give say a 10 millivolt input, I should get a minus 100 millivolts, so minus 0.1 volt output. So no problems there. Now suppose I have another such circuit, again a 1K, and I directly connect these two. What should the gain of the composite circuit be?
It's 1 volt.
Yes? Sorry, I couldn't hear you.
100.
1 volt.
100, right? Minus 10 times minus 10. Now, this kind of coupling we have to do all over and over again various times. The only problem with doing this coupling directly is that this input impedance to this circuit is really not. Input impedance to the op-amp may be huge, but as far as the external source is concerned, whatever this external source is, in this case, is another amplifier stage, that could be anything. What that sees here is really not the op-amp directly. It sees a 1K resistance between this point and this point, which is the virtual ground, right? This point is a virtual ground. So you get a 1K resistance between this point and the ground. So basically, from an external observer's point of view, from an external source's point of view, the circuit actually has an input impedance of 1K. Now that's not a huge input impedance. Now in this circuit, thankfully the output impedance of the op-amp is very small, so the 1K is actually much larger than that. But if instead of using an op-amp here, you have to use some other amplifier, which has a gain of minus 10, but which has, say, an input impedance of, say, its output impedance is, say, 100 ohms. Then what will happen? Then this overall gain will not be 100 despite the fact that you want it to be 100 minus 10 times minus 10. Because you have a 100 ohms output impedance here and a 1K input impedance to the next stage, whatever this output provides, that gets cut down by a factor of 1 by 1.1 when it becomes its input here. And then what will happen is the gain will not be 100, it will be 100 by 1.1. Say a bit smaller, around 90. A bit more than 90, but around 90. Now that may be a disaster if you are using this for precision mathematical calculations. Remember, one of the major uses of op-amp circuits is to be able to do precise mathematical calculations. We showed you how to solve differential equations using that. There, of course, we had integrator stage after integrator stage after integrator stage, and we had assumed that the output to one gets fed directly to the input of the other, and you can use the same formula over and over again. The problem is, there we ignored loading. We said that whatever the output of the one is supposed to be, that stays the output, and that gets fed as the input of the second one. But if you connect the second stage is going to draw current from the first stage, and that is actually going to change the current which is actually fed in, or the voltage that is actually fed in. And that could become quite a disastrous thing if you are using this to do precise calculations. Say, you want to guide a intercontinental ballistic missile using a real-time computer, using op-amps and stuff like that. You don't really want even a fraction of a percent error, because that would end up putting the missile somewhere else entirely. So, or even if you had some less dangerous application in mind, the basic idea is you need precision. You can't afford loading of one stage by another to change your results. So in an actual calculation, you would not really connect an integrator directly to another integrator. You would connect an integrator to another integrator through a buffer. You will put a buffer in between just to isolate the effects of one stage from the other. Does that answer the question?
Yes, sir.
In fact, at a discrete level, you have something called a common collector amplifier, also called an emitter follower. We did not really describe that kind of amplifier a lot, but you can read that up easily in any book. That kind of amplifier also has basically the same feature, that it produces a gain which is actually smaller than 1. This one is 1. For a common emitter follower, the gain is slightly smaller than 1. But that slightly smaller than 1 gain comes at the advantage that it produces a huge input impedance and a low output impedance. So very often you use an emitter follower as an internal buffer stage between two amplifier stages, or between one amplifier stage and the speaker, and so on. Okay. Any further questions?
So, sir, I wanted to ask that under what condition the virtual ground concept holds?
Okay, that's a very important question actually. So let's just point out this. First of all, virtual ground essentially means what? It means that VD, V plus minus V minus, is actually given by VO by the gain, top and gain. This formula works only in the linear region. And because of this huge gain A, this works only when VD is nearly zero. Okay, very nearly zero. Now, how can VD be zero? The first point is VD cannot be zero just by connecting things haphazardly and hoping and praying it's going to be very close to zero. So if you have two independent inputs put in the two ends here, except by a very, very big fluke or except by very, very careful manipulation, you will never get VD equal to zero. So to get VD equal to zero, what you have to resort to is what is called negative feedback. Negative feedback means you take the output, take a fraction of the output and feed it back to the negative input. So that whenever the output tries to rise, V minus goes up, VD goes down, and it tries to pull the output down. Okay, at least does not allow the output to rise as much as it would have. Of course, if the output were to rise without bound, it cannot really rise without bound. What will happen is it would rise and get saturated. If you want to prevent that, if you want to keep the op-amp working in the linear region, the only thing you have to use is negative feedback in some form or the other. So without negative feedback, without a part of the output being fed back to the input, there is no possibility of, or at least there is very remote possibility of you are achieving VD nearly zero, or you are achieving the result that op-amp will work in the linear region. So negative feedback is a must. But that is not enough in the sense that you have to have enough negative feedback. Okay, let me just work with the simpler circuits to begin with, the inverting amplifier. Let's say 1K and 10K we are putting here. And we are asking questions like, I've already done this in the video, but I think there's an important question. So it should be asked again. Suppose I give a 30 millivolt input. And this is VO. Now you all know that the gain for this is minus 10 for this circuit. There is the op-amp gain here. I'm talking about the gain of the circuit, which is minus 10. And so VO, given VI is 30 millivolts, VO has to be minus 0.3 volts. So the formula tells us that. But rather than rely on the formula, let us just take a look at what happens in the circuit, stage by stage. So first of all, we want to figure out how much is the current flowing through the 1K. Anybody tell me that? How much current flows here? The beauty of op-amp circuits is that usually you can analyze them just on the paper itself, just by drawing a few arrows and stuff, and most of the calculation can be done in your head or in a simple calculator. So how much is the current here?
So 30 microamperes.
Yeah, that's 30 microamperes. And how do we know? We know because 30 millivolts is the voltage here. But that's not all. The important thing is, this point is really at ground. So that's actual ground. So for the time being, I'm leaving aside the question as to what do you need for virtual ground. Let's assume that virtual ground really has occurred. So if this is 0 volts, this is 0 volts. So the all important thing about Ohm's law is Ohm's law says voltage across a resistance. That's important. Not voltage at one end of a resistance, but voltage difference across a resistance. That's a trivial thing to talk about. And most people would say that's something they've learned in class 8 or 9 or whenever they first read Ohm's law. But frankly, very few people actually understand it or use it in real applications. Most of the confusions which occur because people use voltage at one end rather than voltage across. Here, voltage at one end is actually equal to the voltage across because the voltage at the other end is 0. So 30 millivolts across this, divide by 1 kilo ohm, and milli by kilo is micro. So 30 microampere is fine. How much is the current here?
It's the same,
Has
30
to be the same
microamperes.
because the op-amp hardly draws any current. Op-amp draws nanoampere order current, which is 10,000 times smaller than this one. So now what will the voltage drop across the 10K resistor be? That will be 30 milliamperes into 10 kilo ohms, which is 300 millivolts. But that's a drop. This end is a 0 volts. 300 millivolts drop means this end is at minus 300 millivolts. So which is this of course is just for the specific example, a derivation, so to speak, of the gain equal to minus 10 formula. That's exactly how you derive the gain. But let me just point out that if you were to change the input to 3 volts and repeat the calculation, so how much would the current here be if this were 3 volts?
Three milliamperes.
So how much current here?
Same, 3 milliampere.
Three milliampere again, right? So how much is the voltage drop across the 10K resistance?
Thirty volts.
Right, and what should the output be then?
It should saturate at the plus VC.
Yeah, but the point is, Ohm's law tells you it's minus 30 volts. You're saying it should saturate. So did Ohm's law suddenly go wrong?
So the op-amp is not in the linear region anymore.
Yeah. So the basic point is, your assumption, the basic assumption that we started out with is, if this end is a 3 volts, the other end is a 0 volts, then Ohm's law tells you this is 3 milliamperes. But this other end is a 0 volts, that's the virtual ground assumption. That assumption gives us an obviously wrong answer. It tells us that the output will be minus 30 volts, whereas we know that the output cannot go beyond minus 12. In fact, it won't even go to minus 12, it will go to somewhere around minus 11.5 or so. So basically, this statement that VD is negligible, this works only in the linear region when the op-amp is actually behaving like an amplifier, that is, this output is proportional to the input. But the op-amp actually can go to the nonlinear region where the output saturates, either at plus 12 or minus 12 volts. And here, if you start from the assumption that op-amp is in the linear region, you end up with a result which says that the op-amp cannot be in the linear region because the output is too big. So you have a contradiction. So how do you resolve the contradiction? The contradiction can be resolved only by saying your initial assumption was wrong. Your 0 volt assumption here, that fails. By the way, can you now tell me what the actual current to the 1K resistance is? Can't be 3 milliamperes. 3 milliamperes would be a disaster. It would give you a minus 30 volts output. How much is the actual current? Assuming that the saturation voltage is minus 12 volts. Yes?
Sir, 15 by 11 milliampere.
Yeah, it will be 15 by 11 milliamperes, simply because you will have to notice this, that this and this, 1K and 10K, are effectively in series because the op-amp draws no current out. So that's an 11K resistance connected between 3 volts and this end and minus 12 volts in the other. So there's a 15 volt drop. So 15 by 11 milliamperes will be the current flowing through your 1K 10K combination. And then you can also figure out what the voltage here will be. It will not be 0 volts. It will be to figure this out, what you need is a drop across the 1K resistance, which of course is 15 by 11 volts. 15 by 11 milliamperes flowing through 1K will be 15 by 11 volts. And that is a drop across 1K. So the voltage here will be 3 volts minus 15 by 11. That's 18 by 11 volts. So that's a drop. That is the voltage at V minus, which of course is nowhere close to V plus, which is 0. V plus of course has to be at 0. It's grounded, actually grounded. So V minus is 18 over 11 volts, very different from 0. VD is huge compared to what it needs to be in the linear region. So this is not in the linear region, and VD is negative, so you get minus 12 volts. Everything works out. Okay. The point I'm trying to make is this. You need negative feedback to be able to get virtual ground. But that is only within a limit. If the input is too big, or, well, if the input is too big for a given amount of negative feedback, or if the negative feedback is too small for a given input, it will not be possible for negative feedback to put the system in the linear region. Okay, and then virtual ground will no longer work. But the easiest way to check whether this is whether you are going to have virtual ground or not is simply to assume you have virtual ground, do the calculation with that, because that's pretty straightforward, and get the output voltage. If the output voltage predicted is within plus minus Vsat, then your virtual ground assumption is okay. If it's outside the plus minus Vsat range, then your virtual ground assumption must have been wrong. Of course, then if you wanted to find out the actual currents in the circuit, you would have to redo the calculation all over again, dropping the virtual ground assumption and assuming that the output is either plus Vsat or minus Vsat, as the case may be. Okay, when I say as the case may be, if your output predicted is minus 20 volts, then the actual output should be, output predicted assuming virtual ground is minus 20 volts, then your output voltage should really be minus 12 or minus Vsat. So that's the easiest way to figure out whether virtual ground will be there or not. You just assume it is there, calculate with it, and see whether everything is consistent. If your output voltage turns out to be within minus 12 and plus 12, then whatever assumption you made at the beginning is fine. You do have virtual ground. Is that okay?
Yes, sir.
Okay, anything further? By the way, let me also remind you, for JFETs, you don't have any of these pre-prepared videos. The JFETs are all in the discussion classes. So of course marked on VLearn anyway. So that's the other part of the class test apart from op-amps.
So would you suggest a book for JFET?
Any electronics book would do. In fact, we did have a bunch of books in the reference at the very beginning, right? Malvina would do, Boylston would do. In fact, Boylston would do perfectly.
Okay.
I think that all these were in the reference at the very beginning of the VLearn page.
Yeah, yes, sir.
Boylston would do perfectly. Malvino also would do nice. But if tomorrow is the class test and you're looking for a book today, well, best of luck. Okay, anything else? Fine. So then I must wish you best of luck for tomorrow's exam. I don't really want to start anything new today. 2 digital electronics videos are up. I don't expect anybody to study them before the class test, but after the class test, please take a look at them. one of them is something which all of you have already known about. So I'm pretty sure it will be at best a recapitulation for you, because most of it is something which you have already studied in class 11, 12. The basic Boolean algebra stuff, things like what is and what is or and stuff like that. Most of the first video essentially the recap. The second video uses something or talks about something called the Karnaugh map method for simplifying Boolean expressions, which is something which some of you may know about, but I'm pretty sure most of you don't. And that happens to be a very, very powerful method. Study that thoroughly, because that's going to be very, very important, not only in this course, but in the next course as well, in the labs, for example. So the Karnaugh map technique is a very nice technique. I've tried to explain it rather extensively in the video, but once you see this, you may have questions about it. So we will do some calculations, and that is some example calculations and also some possible question discussions in Thursday's class on Karnaugh maps and also in other Boolean aspects. Okay, so if there are any further questions, please ask. If not, we will wind up today.
Sir,
Yeah, go ahead.
sir, can you just explain that part where like the two unity buffers and like the output becomes like 1.1 times like less?
No, we did not say two unity gain buffers. We said, let's say we have two amplifiers one after the other. Okay. And this amplifier has a 1K input impedance. This amplifier has a 100 ohm output impedance. There's a unity gain buffer involved here. Okay. How you construct these amplifiers is up to you. That is, you could construct these amplifiers using standard op amps. You could use something else. But you have two amplifiers, let's say, both with gain -10, and this one with an output impedance of 100 ohms, this one with an input impedance of 1K. Of course, if they were identical amplifiers, this one would also have an input impedance of 1K, but I'm not worried about that right now. I'm just worried about what happens when I join these two things together. So I will have to take a look at output impedance of this one. Remember, as far as this one is concerned, this is the source. As far as this one is concerned, this is the load, right? Although we use the word source and load typically for signal source, say the microphone or something, and the load for what is finally going to be the load, maybe a speaker. But as far as these two amplifier stages are concerned, for this one is the load, and for this one is the source. Okay, so what you have done is you have taken a source with not too low an output impedance, not too low an impedance, and connected it to a load which doesn't have too high an impedance. So what happens is, although theoretically, if this were isolated, if this were not connected at all, if I give Vi here, you would get -10 times Vi at Vo. That's what you would expect. However, when you connect these two together, what will happen? What will happen is this voltage -10 Vi actually gets dropped across the 100 ohms and the 1K. And what this second amplifier actually gets is 1K divided by 1K plus 100 ohms times -10 Vi, right? It doesn't get -10 Vi, which is the output from the first stage. The whole of the voltage does not fall here, because the moment current flows, there will be a drop across 100 ohms, so you will get less of the voltage here. Okay. So now, if this amplifier has a gain of -10, it's going to amplify by -10, but what will it amplify? It will not amplify the output for this stage. It will amplify what it gets. And what it gets is this. So instead of 100 Vi, which is what you would expect in two -10 stages, you'll get 100 Vi by 1 by 1.1, because that's what this ratio is. The 1 by 1.1 was just an example with these numbers. Okay? Clear?
So minus
Yeah.
10 VI is dropped across both 100 and 1K ohms.
Yeah, it dropped because minus 10 VI is what the output would have been if suppose, so this is basically internally, if you look at the output side, this is minus 10 VI and then you have the ZO which is 100 ohms. So this is what the circuit really is like. Okay, you have VI on this side, input voltage. Minus 10 VI is what the output would have been if there had been no current drawn. So if the load were infinitely big, no current would be drawn, the load would see exactly minus 10 VI. But what it does see is this. You have a 1K connected across the source, right? So the minus 10 VI would be dropped across the 100 ohm and the 1K. But of this, only the voltage drop across 1K, that's what goes to the other amplifier. It doesn't go. This part is inside the first amplifier. This doesn't contribute to the input of the second amplifier. The second amplifier only gets the voltage across this, which is 1K divided by 1K plus 100 ohms times whatever that is. Remember, amplifier, when you look at it from the source side, it looks like a input impedance Zi. On the load side, it looks like a voltage gain times Vi and then a ZO. That's what we are using here. Does this make sense?
Yes, sir.
Okay, and one more thing, of course, the gain here is of the order of 90 or so, but you have to be careful. Then your input voltage should not really be very big because, say, 1 volt input would not even anyway have even given you a 90 volts output, right? If you are using op amps at least, it would go into saturation. But a 0.1 volt input would give you a 9 volt output and not a 10 volt output as a gain of 100 would have predicted. So in order to prevent that, the unity gain buffer actually comes in here. Instead of directly joining the two, you put in a unity gain buffer in between. And what that unity gain buffer does is that since it draws so little current from this load, this is really like you're connecting a infinite resistance here. So all the voltage, minus 10 VI, will be dropped across the input of the unity gain buffer. And then the output of the unity gain buffer will be exactly minus 10 VI. Okay? Whatever you had minus 10 VI on this side, the minus 10 VI goes on the other side. No current flows into the unity gain buffer, so no drop happens across the impedance of 100 ohms. But then, as far as the next stage is concerned, is the unity gain buffer, which is actually the source for the next stage. And there the output impedance is very, very tiny. So almost no drop occurs, despite the fact that the current can be substantial. You have a 1K input impedance of the last stage, so it's going to draw current. But because the output impedance of the unity gain buffer is so small, so there what happens, in the input stage, it looks like 100 ohms gets connected across infinity. In the output stage, that is for this one, it looks like you are connecting a 1K resistance. Sorry. It looks like you're connecting a 1K resistance, which is, I'm talking about the second stage now. When you are talking about this coupling, it's like you're connecting a 1K resistance, but here is no output impedance, so almost 0 ohms. So whatever voltage you see here, which happens to be same as minus 10 VI because of the fact that this gain is unity, that entirely gets dropped across the 1K. That becomes the entire input to the second stage. Is that clear? So if you're given the input impedance and the output impedance of amplifier stages and asked what happens when you connect them together, you have to be careful. You have to be careful in the sense that whatever gain you would have nominally got from the first stage, that entire output voltage does not necessarily become the input to the second stage because of this potential division. The unity gain buffer essentially ensures that whatever output comes out of the first stage, that gets fed as the input to the second stage without effect of any loading, without effect of any drop. Simply because no current drawn, so no drop here. And current is drawn here, but there is no resistance here, so no drop again. Okay? So the unity gain buffer is what you have to connect in between in order to prevent the loading. That's what the buffer's job is. So despite the fact that it apparently does almost nothing, it actually does a very huge thing as far as practical applications are concerned. Anything further?
So, sir, it is almost like if we like broke the wire and still got the same potential difference across the two ends. It's almost like that.
Yeah, but if you broke the wire, you wouldn't get it, right? So that's the point.
Yeah, right.
It looks like a broken wire in the sense that it essentially behaves as if the two sides are not connected at all. But somehow magically transfers, not magically, but if it really were a broken wire, it would have been magic. It transfers the voltage from one end to the other, which a broken wire would never do, right? So as far as loading is concerned, it looks like a broken wire. But as far as voltage transfer is concerned, it magically transfers voltage from one end to the other. That is, whatever voltage is here, that appears on this side. But the two are, and that is, okay, the broken wire, example sounds like, the simile sounds quite okay, because essentially that's what it does. It isolates the two from each other. So you know why it's called a buffer, right? This word buffer, at least most of you have met this definitely in chemistry, but it's also a very important word in political science. It means the same thing. A buffer state is a region between two countries, possibly two hostile countries, which essentially isolates one of them from another so that you don't get it. They don't come in close contact and get into a fight. Okay. And buffer in chemistry essentially is a mechanism by which you isolate the effects of changing whatever components you have so that it doesn't really reflect that much in the pH. The pH stays more or less stable. Buffer essentially is an isolator. You isolate the cause from the effect in a way. Okay. Anything else?
Sir?
Yeah.
So you said that like we need these devices for high precision applications.
We don't need this always, but we can use them. In fact, op-amps are actually short. The name op-amp is a short for operational amplifier. And there the operational, that word actually means mathematical operations, as we discussed. You go to integration, differentiation, solving differential equations, etc. with op-amps. But if you are going to use them, especially when you use analog computers, that is, computers made of op-amps meant to solve specific problems, you use them in situations where you need high precision as well as very rapid response. There, depending on your application, you would need high precision. Depends on what your application is. Of course, when I say high precision, it cannot be a blanket term. You may have applications where some amount of error is fine. But if you're controlling, say, a drone or a missile or even an aeroplane using things like this, you wouldn't really want the precision to be low. Right? So what exactly was the question about this? Yeah.
So I was asking like, so like we first of all use the H parameter equivalent, I guess, here, right?
Not really. You mean can you use the H parameter equivalent for an op-amp circuit? Is that your question?
Yeah. Like even for a normal amplifier, we replace it. No, sorry, with for a transistor, we replace it
Yeah,
with
we do
a
that,
H. So even
right?
an H parameter equivalent is an approximation, and then with the transistor
Yeah,
also, that is also an
true.
approximation.
But okay,
So
let me make one thing very clear. Approximations are important and they are part and parcel of whatever you do in physics. The important thing is approximation has to be controlled. You should know what kind of errors are involved there. So when you say high precision, it depends on what your application is. For some application, the H parameter equivalent results is fine. For some others, it's not. Okay. So if you want very high precision involving a transistor amplifier, maybe the H parameter equivalent will not be good enough. Then the H parameter equivalent would be a good enough starting point to give an indication what the circuit will do. But if you wanted to know whether the output will be exactly 3.10 volts or 3.11 volts, you may have to resort to more precise modeling of the transistor. Okay. That being said, the op-amp actually has a very clever design. Op-amp, after all, is made out of transistors inside. Okay? Not discrete transistors, but transistors which you built into a silicon chip so that you make everything into one circuit. But it has, unfortunately, discussing the internal construction of an op-amp would be too time-consuming for this course. We don't really have that much time in this course. But it's really the fascinating subject as to how you can actually make a device which behaves very, very precisely, despite having been built of components which are really not so precise themselves. So you have lots of special circuitry magic going on inside, which is actually very fascinating, but frankly too lengthy to discuss here. But apart from that, notice that once you've constructed the op-amp, the basic idea is the op-amp has a huge, huge gain and a very low output impedance, very high input impedance. That's how it's constructed. Now, when you couple that with negative feedback, you can essentially see that you can get very precise results out of it. The point is the gain is huge, okay, but the gain is also rather imprecise. But let's say, I will just, I think I've already also discussed it in the video, but the voltage gain of an inverting amplifier will not really minus R2 by R1. I forget exactly what the formula should be with a finite gain op-amp. I can calculate that, but let me just, you can try calculating that yourselves anyway. But most likely it will be something like this. So the op-amp is built out of imprecise components, and it is imprecise in the sense that AO can be very fickle. It can change from 10,000 to 100,000. Sorry, this of course is wrong. This cannot make sense. This cannot be correct. Maybe this is correct. I'm guessing here. I can work it out, but anyway, you should realize why the previous one was obviously incorrect. The previous one had a resistance added to an inverse gain, and resistance, of course, is dimensional. The inverse gain isn't. So that's an illegitimate statement. But maybe it's something like this. I'm not sure it is this. It's not exactly this. Doesn't matter. This captures the right idea. The point is the circuit components are imprecise, and AO will be pretty fickle. It can go from 10,000 to say even 100,000. But as far as the gain of this circuit is concerned, will that matter much? Note that you get 1 plus 1 by 10,000 or 1 plus 1 by 100,000. This 1 by 10,000 is already so tiny compared to the 1. Whether it changes to 1 by 100,000 doesn't really matter. You get almost exactly the same gain. Okay. So the huge gain, huge though imprecise gain of the op-amp, coupled with negative feedback, ends up giving you a nearly precise circuit. Ultimately, I don't care how much the op-amp amplifies. What I care about is what does your circuit really do? Here, your circuit gives you amplification, which is not, this is approximate, this is exact actually. Sorry, I should really have written the A in the middle because, okay, please don't take me up on this expression. I'm pretty sure this expression may not be correct, but it has the right idea. But in fact, I'm pretty sure I've already discussed what this should be in one of the videos, but you should be able to work it out yourselves anyway. But the point that I'm trying to drive home here is this. Your circuit components are imprecise, your analysis may be imprecise, but it doesn't matter. There's 1 by AO. Say you analyze using H parameters and end up getting a getting an AO of around 20,000. But as you're rightly saying, the H parameter approximation is an approximation which may not be very precise, but actually it is quite precise. But even if it's not, the 20,000 may change to 15,000 or may change to 40,000. I simply don't care. Your output will still be minus R2 by R1 times the input, because whether AO is 15,000 or whether it's 40,000 doesn't matter. The whole point in good electronics design, in fact, the whole point in good engineering design anywhere, is to know that you're dealing with imprecise components. So you design in such a way that even if your components go this way or that a bit, your design will not fail. When people design a building, they design it with certain amount of strength of materials in mind, how much load the concrete will bear and so on. Of course, real concrete does not match those ideal numbers. But the design is made in such a way that even if your parameters were off by quite a bit, your final behavior of the final output system, that should be the same. You don't want your building to collapse just because somebody used another sack of concrete, which was of an inferior quality. Okay. Of course, if you entirely use inferior concrete, your building might collapse. But the buildings are designed in such a way that small fluctuations in the parameters will not really affect the final thing. That's for civil engineering, but that's for every engineering. By engineering here, I mean trying to construct real application things out of physics principles. Basically, these are physics principles, but these are not physics principles where you can hope that everything will work exactly perfectly because my theory says so. You have to build it into the design further fail-safes. That is what is done in an op-amp design anyway, at a much smaller scale. It will still work even if your parameters were not right. So the H parameter equivalent approximation, you have to realize that what you are doing is you are using an approximation. But you should also know how good or how bad the approximation is. And for most small signal applications, it's perfect. Okay, perfect is not the right word to use perhaps, but it's as perfect as you want it to be. But for other applications, it may not be, but then you have clever ways of working around that. Okay. Any further questions? Okay, if not, let's call it a day today. I'm going to mail you the question paper by 2 p.m. tomorrow. And I hope I don't goof up again and forget to create the link. In fact, I think, okay, I may not even mail you. So be careful. I will just let you know in the morning because it might very well be that you would have a quiz on VLearn itself, if I can manage to set everything up right. Okay. So if there are no further questions, okay, I'm feeling like an auctioneer here. I could try a going, gone kind of thing. It seems that nobody wants to ask a question, so let's stop the recording.